All right, one more quick example. So this is an example I found on about the pendulum. We all know and love the pendulum, right? So in this problem, we'll have two states. We'll have velocity and the angular position. So the angular velocity, angular position of our pendulum, and then we'll also have some. You can see my mouse. We'll have some control input U, which pushes the torque, which induces a torque into our system. And then we'll have a couple parameters. These might be a little bit different than what you saw in class, but we'll have one parameter called lambda, which is the damping coefficient. So lambda is greater than 0. Let's go ahead and just write that down here. So lambda is greater than 0. And then we'll have the other one, omega squared. So omega squared is greater than 0. Great. So if we put this into state space form, so let me make some adjustments here. Great. So putting this into a state space form, we can define x1 as equal to phi and x2 equal to phi dot, right? Basic thing. I'm not going to go through it because we've done this before. But this leads to, we'll get x of t, which is equal to x1 and x2, right? Let's put dots on all these, which will be equal to phi dot and phi double dot, which is equal to x2 and minus lambda x2 minus omega squared x1 plus this input that we'll be defining. Okay, so this will be equal to our f of x and alpha. So this is right here is because we set u is equal to the control that we're defining as lambda squared. Oh, it's catching up. Great. All right. So now let's introduce the payoff. So the payoff is given by P of alpha, which is equal to negative 0 to tau 1 dt, right? So this is equal to negative tau. Right, so what does this mean? So this is for tau equal to tau of alpha, which is equal to the first time that x of tau is equal to 0. Which we could think of as essentially phi is equal to phi dot is equal to 0, right? All right, so we want to maximize P. Right? That's our general framework, which means that we want to, for this particular P, we want to minimize due to the negativity of the payoff. We want to minimize the time it takes to bring the pendulum to rest. Right, but note that this doesn't exactly fit into the problem statement that I initially introduced. Namely, there's no fixed end time, right? So this is called, so let's say due to the fact that capital T is not defined, this is called a fixed endpoint free time problem. Right. So, namely, this brings us to fixing the endpoint at x equals 0, right? But the time at which we allow it to occur is not specified. Right. And that's all I wanted to say. So this results in what's called a fixed endpoint free time problem, because it doesn't fit into the it's a subset of the optimization problem that I introduced before, due to the fact that t here is not defined.